that. Now that's not, that table is not going to be something that would be on the quiz in class. Now it might be on the take home. I don't think I put it on the take home this year. So you don't. There won't be a time on a quiz. It won't be on the midterm or anything where you'll have to write out the table or anything. So again, hopefully you're able to come up with that. And then this last part here, and this won't be on next week's quiz either because next week's quiz is no calculator. But again, just going through the mechanics of Newton's method here. So I've already set this up for number 15. And in part A, you were supposed to go through and find the different ones and find what those roots were. And then in part B, it said what happens if you put in a 2. So we said we could do this. We could put in a 2. And then we could do our shortcut, which was with the answer key. And we could go F of that value, and then down here go G, which would be F prime of that value. And we get, if I hit control enter, we get a 5, and then a 2, and then a 5, and then a 2. Right? You come up with that. And so what's going on there? That's that cycling thing. Now the interesting thing, the other thing, or one of the things we talked about with that then is if I would have started with something really close to 2, okay, just a tiny bit off. If I start with 2, it cycles. But if I start with this and do the same thing, which is this, then I get something really close to 5, and then I get something really close to 2, and then I get something really close to 5, and then really close to 2, and then really close to 5, and then kind of close to 2, and then still pretty close to 5, and then 40, right? So what happened? I mean, so those tangent lines were kind of cycling, but hitting just at a little different spot. So then when they hit the curve, they hit at a little different spot again. But then all of a sudden, what's this mean? It shot that tangent line where that was shooting here is now, that was shooting at like 2 is now shooting way out at 40. So that curve had curved just enough that when it got off of there just a little bit, all of a sudden instead of going here, it went there. And so the farther out we get, kind of like that ripple in the pond, as it goes bigger and bigger, bigger changes, even with a small, tiny initial change. And so all of a sudden we get this. And so now we got the tangent lines crossing, and then eventually we end up, and I assume that was one of them you got in part A. Is that right? Mm-hmm. 6.438. So eventually I found that other one. So tiny change in that initial condition ended up greatly changing what happened. Okay, and then the last one, they give you 1.39. And you go ahead and do that. Now again, always keeping in mind that when we do this when we do this little formula here, what we're really doing is, remember where that came from. That came from the tangent line equation set equal to 0. So again, another idea of Newton's method is we don't know how to solve a fifth degree or a weird sine function or something, but we do know how to solve linear equations. So if we can turn the curve into a linear, that's what the tangent line approximation does. We can turn it into a linear, we can solve it more easily, and that's where this little formula came from. So now I do this, and we get 5,391. So what happened? This was near a peak, wasn't it? This was right up near a maximum or a minimum. And that tangent line shot me way out to the thousands. And, of course, if I go ahead and do it, and continue it, it's coming back, the tangent line, just kind of like that first example we talked about. It's coming back, and it ends up finding the one of the 3 roots that we have there. Also, I talked right past number 5. I forgot. I wanted to talk about part B. I wanted to talk about part B and 5. It said to justify that. Part 5, the one root we found in the table, they said, were there any other roots? And did they give you a hint on that one? No. So this was, what was it? It was x to the 5th. Okay, what was it? X to the 5th. Plus 4x. All right. And so you guys found that you used that initial guess And now in part B it says, is that the only root? And it's not good enough to just say, well, yeah, I looked at the graph and it only crosses what? There's another way. And did I give you a hint on this one?
F prime is never equal to 0.
F prime. If you do the derivative. Now this is really important because there are going to be some packet, midterm, AP, final kinds of questions where this is something you need to think about. And it kind of relates to the theorems we're going to get into today. How many roots does this have? We found one. Now how many could this possibly have? This could have as many as 5. Here's F prime. Look at that equation and tell me what you know about it. Brendan just said one thing. She said it's never equal to 0. Why not?
X to the 4th is never.
Yeah, if you subtract that over and get negative 4x to the 4th can't ever be a negative, right? Or you could look at that. Another way to look at this is as a graph. This is an x to the 4th, which means the tails are going up, right? And then the plus 4 means what? Shifted up. So another way of saying instead of f prime is never 0, f prime is always positive, right? And if f prime is always positive, what's f? Always increasing, which is kind of what she was saying, is that f prime is never 0. Well, if this is going to cross multiple times, it's got to go up and then go down, right? That's the only way it can cross more than once is to go up and go down. Well, if it goes up and goes down, the derivative's got to be 0 on a polynomial because we know it's nice and smooth and everything. And so if it's never 0, then it never goes up and comes down. Again, or you could say since f prime is always positive, f is always increasing. If f's always increasing, it never comes back down. Okay? So it is going to only cross one time. F is going to cross one time. So those are some of the techniques pre-calculator, pre-graphing calculator days that we really had to use to be able to tell what was going on with some of these things. Okay? But that is a justification that we sometimes have to use in some problems. Okay, so that was a good one there also. All right, let's take a look at your packets. So that's kind of it with Newton's method. So be prepared to talk about Newton's method and what's going on with it. And let's go ahead and see if you've got some things we should discuss in sample 2. As we get ready for this midterm, you got to understand that it is difficult, but the more you get through these problems, because what's happening, what the AP test does that I really like, is it makes you go back and think about all the different concepts we've learned. It makes you tie them together and put them together. And as you go through these problems, you're going to say to yourself, there's no way I could have come up with that one. I couldn't have got that one. But the more of them you do, the more you see them and you say, hopefully, oh, okay. Yeah, I remember that. Now, I can try that, or I can do that, but you got to spend time with it. You got it. All right. Somebody got one? Yeah.
I was wondering about 36. I looked at the graph and understood why that was the answer, but I was just wondering if there was a way to justify it without looking at the graph.
Okay. And this is a calculator one, so looking at a graph is fine. Is that one where they give you f prime? I think that's exactly what you want to do. We talked about this one in the other class, and they would ask me to show them on the calculator how you could do an antiderivative, and you can do it, but I'll be honest, I can't think of many times that's very useful for us right now, especially in the template button where where you do the derivative thing. There's this one. That's the antiderivative. That's how you do the antiderivative, something we'll be doing when we get into chapter 5. But it turns out there is an antiderivative for this one, but then when antiderivative, you got to do a plus c, and then that runs into some other issues. And to be honest, most of the time when I've seen these on calculator problems, they pick ones where there is no antiderivative. Now, you might be thinking that seems kind of strange. What do you mean there is no antiderivative? There are actually functions where there is no antiderivative. Now, we can find derivatives of all functions. We have rules for all the different scenarios we could come up with. Now, it might be undefined at some points, but we can find a derivative for all different functions. But antiderivatives, we can't. And the reason is you have to work backwards. I guess you could say it's kind of like square and square root. You can take any number and square it, right? 4 squared, 5 squared, 6 squared, right? You get 36. But does it work the other way? Now I'm talking about with whole numbers, right? 4 squared, 5 squared, 6 squared. Take any whole number, square it, you get another number. Can you work backwards with any number? No, 35 doesn't have a square root. Not that it's a whole number. Why? Because there aren't two numbers that multiply to make 35. Two whole numbers. Well, it's the same thing with derivative. I can give you a real simple one right here. There is no antiderivative of that function. Why? Because there's no function that when you do its derivative will give you that. Right? And that's what has to happen for an antiderivative. So, and there's a lot of them. So this one turns out there was a derivative, an antiderivative, but most of the time I've seen there isn't. So, because what you want to do here is a list of candidates, right? I mean, what you'd like to do, they want an absolute minimum. So you'd like to do a list of candidates, but you have to plug those back into the original, and there is no original. So, Brenda, you've got exactly what you should do. I think you should look at a graph of this, and it turns out what happens, and remember what we get with f prime. It turns out that graph is negative before this number, and that's like 0.6 something, this number right here. And then it's positive up until about 1.6, and then it comes back down. And then it stays negative the whole rest of the time. I think that's what it does. So what we have is a local minimum, a global, or a local maximum, and then it goes down. Well, so think about what this means. Remember, this is f prime. So this means the f graph's going down for a little while, going up for a little while, and then going down for a long, long time. So where's the minimum? Got to be at the input, right? So the f graph is going to go down a little bit, it's going to go up a little bit, and then it's going to go down for a long, long time. And so the minimum is going to be at that far right input, 5, and that's all you need. Again, this is a multiple choice one, so you don't need a justification. Now, if this was a free response and you needed some sort of justification, then drawing a graph or doing a number line and saying just what I said about how it's going down a lot longer and farther than it's ever going up, and so the minimum has to be at the right end. Okay, good question. What else? Free response. Absolutely. Now, on the free response, you can usually count, let's just go through this free response, okay? There are some main big concepts in calculus class, and you can always bet that there's going to be one of each of those on the free response. There's only, on the AP test, there's 6 free response questions. Now, the multiple choice, there's a whole bunch. So they get into all the different details. You got some trig, you'll have some algebra, you have all kinds of stuff. But in the free response, you can always bet there's going to be these main concepts. Here it talks about area. We haven't learned that yet, but we know, we've touched on it a little bit, that we know area is a big deal. So we're going to be doing some area stuff. Okay? You get to number 2. 2, when you read it, talks about, we didn't know enough to do a lot of this stuff yet, but it talks about some temperatures, but it gives it to us. You see this integral symbol here. We haven't gotten into that. So that's another application we haven't quite gotten ready for yet. Okay, 3 is about local max, local min, chart kind of stuff. Okay, that's a big deal. So you can always bet there's going to be some local max, local min, chart kinds of questions. Okay, here's 4, differential equations. Differential equations is another big topic. So you can bet there's usually going to be that kind of stuff. All right, so let's go into this. So any part of this, probably it all kind of ties together, quite honestly. Dakota, was there any, would you ask about Dakota? Who asked about it? Calvin?
Yeah, I pushed on all of them, but I'm pretty sure you
Yeah, well, they all kind of go together. I mean, is there anybody else that feels like we'd be wasting our time doing this one because it's so easy? Okay. Is there anybody else that's even tried this one?
Oh, yeah.
So you read it through and looked at it. Okay.
I
Okay,
opened
good.
my package, shut it, and decided
All right.
that calculus.
Let's go. This would be time well spent. So let's go through this. And it does kind of all tie together. And reviewing, just differential equations in general, I think is gonna be good for you. Now, they say here that the differential equation, they told us, was y minus y squared all over x. Is that right? Is that the differential equation? And they're telling me that this is a solution. Remember, what's the solution to a differential equation? The original equation. So y equals, right? So here it is. And remember, it usually has a plus c in there somewhere, right? Some that we can find if we have an initial condition, that kind of thing. All right? So verify that this is a solution, okay? Now, the way we did that was with the old T-chart. Okay, that was one of the ways you could verify. I mean, I think it's a nice way to organize your work. So over here, we're going to get y, and that's going to be, so that's x over x plus c, minus that squared, so x over x plus c, all over x. So that looks like a mess of algebra, and it is. It's a bunch of algebra, and this is a no calculator. Okay? So I don't know what to tell you, dude. You have to do some algebra. Okay? Y prime. So how do I get that? Take the derivative of this over here. So we're going to do a quotient rule. So derivative of the top is 1. Leave the x plus c alone. Minus the top times the derivative of the bottom, which is 1. All over the bottom square. Now I can simplify this a little bit. This is going to be x plus c minus x. So these x's are going to drop out. So c over x plus c squared. That's about it, right? That's about all I can do there. All right, now, what about over here? Good. Somebody in the air class mentioned that. Did you try it?
Well, I didn't really.
Get that far, did you?
Well, I just, before I plugged in x over x plus c, I factored out y from the derivative and worked it a little bit.
Oh, so up here you had y, and then 1 minus y.
Yeah. So it all just looked a little different.
Yeah, so it's not squared and that kind of thing. I mean, yeah, there's a lot of routes we could go, and then of course when you say factor out an x over x plus c is the same as factoring out a y right there. Bring the x up, and then multiply it through. Get that out of the way. Okay, that's not bad. One of the things I've noticed that we seem to have a little fear of is getting common denominators. We struggled with that when we were doing limits, because that's really what needs to happen up here. Right? This is x over x plus c, and this is x squared over x plus c squared. So the common denominator would be x plus c squared. Right? This has x plus c twice. This has x plus c once, so I can do x plus c top and bottom. Right? I think that's probably one of the cleaner ways to do it, to be honest with you. And then do what Callan said, is bring that x up, I think, too. Actually, if I bring that x up, it could cancel a little bit with one of those as well. So maybe I could do that. Maybe we could go ahead. Let me change colors on that. That might not be bad. If we do this, in other words, really I'm kind of doing that kind of thing is what I'm doing. Right? Multiplying that. So that's up there. Now I got to distribute that to both of those. So this x would cancel that x. So I actually have 1 over x plus c. Right? And now remember, this here is x squared, and this is x plus c squared here. So if I take this 1 over x times that, it'll cancel with that x there. So I have x over x plus c squared. So that cleans it up a little bit. Right? If I bring that x up there. So I have to deal with that. So now what's my common denominator here? X plus c squared. So this fraction needs an x plus c and an x plus c right here and here. Okay? So now I've got a common denominator of x plus c squared. And then what do I have up here? I have x plus c minus x. X's cancel, and sure enough, right? So that would be one way. I could have got a common denominator first. I'd have had some x squared, been a little messier, but it would have ended up the same. And then I could have went the same route that Brenda was saying. I think that would have worked out okay too. I mean, there's just a lot of different things algebraically, different order we could do those things. But that's what they're going to look for. That'd be the work they're looking for to verify. Now, here's the thing. The reason they gave you this solution and they told you to verify it is they want you to use this the rest of the way. So even if you couldn't get this, right, keep going, right? Just say, okay, this is a solution. I know I should have been able to verify it, but I couldn't. And so I'm going to go on and get the rest of it that I can, right? Now, don't forget this. It says show that all solutions contain 0, 0. So all they're wanting you to do is plug in 0, 0. So what you get is, okay, if y equals x over x plus c, if I put a 0 into there, I get 0 over c. And sure enough, 0 does equal 0. Check. So all solutions, all these solutions would contain the point 0, 0. Now, you say, that's kind of a weird question. Why'd they ask that? Well, later on, they're going to ask you to sketch the graph in the slope field. And so this is kind of like a hint that, hey, when you sketch your graph, you better have part of your graph go through 0, 0, right? Because all the solutions go through the point 0, 0. That's what they're saying. So you'll see when we get to that here in a second. All right, go to part B. Write the equation of the particular solution that contains the point 1, 2, and find the value of y prime at 0, 0 for that solution. Okay, so our solution is y equals x over x plus c. That's called the general solution, if you remember. The general solution. The particular solution is what we're going to get when we do what here? We're going to put the point 1, 2 in. So we put 2 in for y, and we put 1 in for x. We put 2 in for y, we put 1 in for x. And then we solve. So we multiply the 1 plus c over to this side. And we get c to be negative 1/2. And so what do I do with that negative 1/2? Put it back in there for c. So I get this. So the particular function that I'm going to be working with, the particular solution to this differential equation with that initial condition, is that function right there. Okay? Now there's another part to this. It says find the value of y prime at 0, 0 for this solution. So what do? I need the derivative. I need to plug 0, 0 into the derivative. Now, I've got two different derivatives I can use. I've got the one they gave me at the beginning, which was y minus y squared over x, right? Wasn't that y prime? What happens if you put 0 and 0 into that? You get 0 over 0. Now, what does 0 over 0 mean to us? Indeterminate. Something else is going on, right? Something else is going on. It's not just undefined. It means something else is going on. Okay? So I don't want to use that. But I had another, I've erased it now, but I had another y prime there, didn't I? Didn't I have c over, back in part A, didn't we have this? Didn't we have this as our y prime? Of course, we now know that c is negative 1/2. So y prime is negative 1/2 over x minus 1/2 squared. Now, you can simplify that, but I actually don't think you have to, because what we really want to do right now is what? We want to put in 0, 0, right, for x and y. Now, there is no y, so we'll just put it in for the 0. So we put in 0, we get what? We get negative 1/2 over, put 0 there, 1/4, right? Negative 1/2 squared would be 1/4. What's negative half over a fourth? Invert multiplied -2. So, all right, now think about what's happened here. In part A, because I'm intrigued by this 0, 0. They gave me the initial condition 1, 2, but they sure seem bent on giving me information about 0, 0. First of all, they said that all solutions go through 0, 0. And now I just found out what? The slope when it goes through 0, 0 is -2. So it's going down. When it goes through 0, 0, it's going down. See, it's like they're giving me little hints along the way, little bits and pieces that I'm going to keep track of here along the way. Because a lot of times these problems do tie together. The different parts do tie together a little bit. All right. C. Write an equation of the vertical and horizontal asymptotes of the particular solution we found in part B. All right, so in part B, we had y equals x over x minus 1/2, right? That was our solution. So they want us to write the vertical asymptote and the horizontal asymptote. This is a great question because, man, this really makes us review and think about a lot of different things that we've learned. So let's do vertical asymptote first. What happens vertical asymptote? What happens at an equation to make a vertical asymptote? When what? Number over 0. A number over like 7 over 0 or something. It's undefined, but it's got to be not 0 over 0, but a number over 0. When's that going to happen here? When x equals 1/2. And of course, that's a vertical line, right? The equation x equals 1/2. So the vertical asymptote on this one is at x equals 1/2. Okay? That's another piece of information. If we're going to graph this particular thing, which I can see we're going to down in part D with that big slope field they have for us, that's going to be an important piece of information. Vertical asymptote at x equals 1/2. Okay, horizontal asymptote. Where do we look for those?
The y value is
Say that loud.
the y value is
As x approaches infinity, we always have trouble with horizontal asymptotes because they're totally different than vertical asymptotes. Vertical asymptotes are when you get something over 0. Now, they both have to do with infinity. Vertical asymptotes are when you get an output of infinity. A number over something really small. That's an output of infinity. Horizontal asymptotes are when the input goes to infinity. What's happening as x gets way out here? So what this is really a limit problem. So you got to look at this and say, what's happening as x gets really big? It gets closer to 1. Remember, the 1/2 doesn't matter. If you have a billion minus 1/2, that doesn't matter. So this is really not even there. X divided by x is 1. And so how do I write it? Y equals 1, because it's a horizontal line. It's a horizontal asymptote. So the horizontal asymptote is y equals 1. So there's another piece of information. This thing I'm about to draw is going to have a horizontal asymptote at y equals 1. Okay, so that reminds us of what we learned about limits back in chapter 4, early part of chapter 4. Okay? All right. And then finally, we can put all this information together. The slope field for the given differential equation is provided. Sketch both branches of the solution curve that pass through the point 1, 2. So, here was our solution. We learned all that stuff about it. We know that it's got a vertical asymptote at 1/2, which would be right in here. So I'm going to put that in. We know it had a horizontal asymptote at 1. So I'm going to put that in. We know it passes through the point 1, 2, which is right up here. So it's going to go like so. Right? They gave us a nice hint here when they said sketch both branches, because you might be tempted to just draw that. if they hadn't led you a little bit through that other work, you might have done that and stopped. But what do we know about this curve? Has to go through 0, 0. In part A, we answered the question that says show that 0, 0 is a solution to all solution curves. So it's got to go through 0, 0. And when it goes through 0, 0, it's got what? Slope of -2. So when this goes through 0, 0, it's going down like so to the vertical asymptote, and then it's coming up like so to the horizontal asymptote, and there it is. Both branches. Everybody okay with that? Now, in the other class, there were several people bothered by the fact that it says the solution curve passes through 1, 2, and yet this does not. Over here, right? So here's how I explained that. This is one curve. This is one curve. Okay? So you can't think about it as two curves. Kind of the same rationale would be this. You know, if I gave you a parabola and you thought about this as this branch and this branch of the parabola, you can't think of it that way. You got to, you know, if this was the point 2, 7, and I ask you, does this parabola pass through 2, 7? Yes or no? Yes. Okay? But somebody else might say, yeah, but this branch doesn't. Well, it doesn't matter. Altogether, it's one curve. This curve passes through that. Well, it's the same thing over here. Okay? This is one curve. Does this curve pass through the point 1, 2? Yes. Right? Yes, it does. Okay? It's just that the curve is made up of more than one branch. Okay? So that's how you have to think of it. All right? Because you can't have a curve with two branches where both branches pass through a point, right? I mean, it couldn't happen that way, right? It wouldn't be a function because there'd be overlap and stuff like that. So you got to think of that as one curve, even though it's multiple branches. Kind of like a hyperbola is one curve. Okay, it's got two, because that's basically what we have here, hyperbola. Okay? All right. So that is that question. Pretty tough. I mean, but could you get parts of that? I would hope so. You know, even if you couldn't get all those things to come out, you know, certainly there'd be some points to be gotten there. And you know, on the AP test, now on our AP test, we're not going to be able to do all parts of the free response questions, you know, because we haven't learned all those different things. Once we get to the end of the year, the free response questions on the AP test are all worth 9 points, and it's not unusual for the national average on some of those questions to be 3. You know, the national average is people get like 3 out of 9. An easy question would be one where the average is maybe 5.5 to 6 out of 9. You know, although many of you will get all 9 on some questions, I don't have any doubts about that at all. But you know, there might be some where you know you go and you get 1 point or 2, and that's the best you can do. So you know, we just want to keep working to get as much of that as we can. All right, we got time for another one. Let's do one more. 5 on the free response. We could do that. This is a good one. There is definitely some trick. Now, I have noticed in recent years on the AP test that the level of difficulty of the trig stuff has went down, I think, a little bit. So this would, as we go through this one, you'll find that there is some trig stuff that gets kind of tough. Not too tough, but if you don't see certain substitutions you can make, it makes it harder. So anyway, here we go. We're going to do what with this to start? We're looking for y prime. So implicit differentiation. So what's the derivative of tangent y? Secant squared y times y prime equals 1 plus y prime. Now, you're supposed to find terms of y, which means the answer will have y in it. The answer will have y in it and only y. So I need to group the y prime terms on one side, so if I move that other y prime over here, okay, like that, now I'm going to take out a y prime. And then divide. Okay, and that is good. Right there. Now, because I've got y prime in terms of just y. So that's probably worth a couple, 2, maybe 3 points right there. So that's good. Now it says, find the x and y coordinate of each point where the tangent line is vertical. So this kind of connects to what we were just doing. The tangent line is vertical means what? The slope is a number over 0, right? So in other words, when that bottom is 0. So we've got to solve that. Okay? So secant squared minus 1, where does that equal 0? So that's what we're trying to do there. Okay? So, secant squared, and this is again a no calculator. So secant squared y minus 1 equals 0. So that'd be where secant squared equals 1. I hate working with secant squared. What could we do with that? 1 over cosine squared, right? So then if I multiply, oh, it's nice if that's 1. 1 over cosine squared equals 1, so I multiply it over. So it's really, where does cosine squared equal 1? Right? Which is like saying, where does cosine equal plus or minus 1? Right? And so where does cosine equal plus or minus 1? Well, that'd be at 0, at pi. But yeah, now notice x is supposed to be from negative 2 pi to 2 pi. Now that's not y, that's x. Now, it turns out they'll be the same, okay, which we'll get to here in a second. But you might not have known that, but at least that would be a place to start. So it looks like y is going to be negative 2 pi, negative pi, 0, pi, 2 pi. It could be any of those, right? So 0, pi, 2 pi, negative pi, negative 2 pi. Those are places where cosine would be plus or minus 1. Okay, now it says find both the x and the y coordinate of each point where the tangent line is vertical. So that's the y coordinate. How do I find the x coordinate? Got to go back to the original. So the original is tangent y equals x plus y. Well, this is going to be a real mess because I got all these different y's I'm going to have to plug in. Well, one thing that turns out pretty nice, actually, is what happens when you plug all of those into tangent y. I know. Well, eventually I'm going to get the opposite. On this side, I just get 0, right? Because remember, what's tangent y? It's sine over cosine, right? Tangent is sine over cosine. Well, at all of these points, here and here and here and here and here and here, what's sine? 0. So sine over cosine is going to be 0 over something, so it's always going to be 0. So this side is, no matter what I plug in there, any of my choices, that side is going to be 0. So x plus y is this, so x is just negative y. X is always going to be the opposite of what y is. So if those are my y's, so my x's are just opposite. So if I have negative 2 pi for x, my y is going to be 2 pi. If I have negative pi for x, then y is pi. If I have 0 for x, y is 0. If I have pi for x, negative pi for y. And 2 pi for x, that's negative 2 pi. So x and y coordinate, so that turned out to be a little easier than I thought it might end up being, where I didn't have to plug each one in individually and solve for x. Okay? So at those points, this curve is going to have a vertical tangent line. Okay. Now, the last part. What do those 2's mean? Second derivative. All right. So I know y prime is 1 over secant squared y minus 1. So how do we want to do that? That's how we'd love to do it. Use our calculator. I think a better way than quotient rule, I don't like to do quotient rule when there's just a constant on top. I'd rather do this and make the whole thing be that. Okay? But there is a nice thing. Robbie, go ahead. What were you going to say?
I was gonna ask, secant squared minus 1, is that just tangent squared?
It is just tangent squared. And that's a really nice thing to know. Now, if you don't know it, okay, you don't know it. There's not much you can do about it. It comes from this. Sine squared, this is hopefully one we all remember. Okay? And I'll be honest, I even have trouble remembering the secant squared. I know there's a connection between secant squared and tangent squared, but I can never remember what it is. So I always come back to this. All you have to do is take this and divide by cosine squared everything. And what do you get? You get tangent squared plus 1 equals secant squared. So secant squared minus 1 is tangent squared. So what that allows you to do, and for time's sake, I'm going to go ahead and do that, is make it be this. Now, you could do this derivative here, or you could remember that 1 over tangent squared is just cotangent squared. That might be just as easy, but this isn't too bad, so let's go ahead and just work with this one. Okay? Now, you do have a power on a power here, so probably the smart thing to do would be to write this as tangent to the what? -2. Now again, we're getting into a lot of different little algebra tricks and stuff that you might have seen or might not have seen. So, you know, there could be about 8 different ways right now we could have proceeded here with this, right? Some people could have done quotient rule in this. Some people could have just went with this. Some people could have just went right here. We could have called it cotangent. We could do this, you know. I mean, so who knows what you'd have thought to go down, what road you would have chosen to go down, but a lot of these problems have 7 or 8 different paths you can take, and eventually they'll get there, okay? All right, so now when I go to do y double prime, bring down the -2, leave the tangent alone to the -3, times the derivative of the inside. What's the derivative of tangent? Secant squared y, and don't forget to tack on y prime. Now that brings up one last little bit, as if there wasn't enough here already. The directions just mean get it in terms of y. We're not quite there because we got a y prime there, but what do we do then? We know y prime is, well, any of these. This right here is y prime, isn't it? Okay, this right here is y prime. So I could just take that and stick that right there. Okay, and so I still end up with, then I end up with something that's just got y's in it. So,
Stop there, or we can
No,
simplify it?
I typically just simplifying algebraically and the final answer is not important. So when it says find second derivative in terms of y, once you have it all in just y's, you're good. Yeah. So you're right, because this would be a tangent to the -2 with a tangent to -3, that'd be tangent -5, for example. And not only that, but then tangent's got some sines and cosines in it, that's got some cosines, so we can do that. I mean, there'd just be tons of ways to write this one. And, you know, this would be one I remember when I was grading AP tests and we'd go through this, there were just so many possibilities. You really had to work with them every step of the way to see how they were going through it.
So these are the ones that you look at and you go, I don't even want to grade this.
Yeah, this is going to take a while. Yeah, so that one, a lot of different trig things in there. So, all right, let's move on here. We've got something in chapter 4 to talk about. Just a couple little things to be wrapping up here in chapter 4, and so we've got that quiz on Wednesday, but we're going to be working in packets and doing that. Midterm is probably going to be, yeah, if I had to guess right now, I'd say the first day of it would be next Friday. That's kind of what I'm leaning towards. So that's a big part of our focus over the next week, but we'll just keep working on this stuff. So let's take a look at probably getting your notes out here, and I'm going to tell you 2 of the questions on next week's quiz.
Are you gonna tell us the answers too?
I'm going to tell you, oh yeah, good. Yes, it's even better than just telling you the questions. I'm telling you the answers as well.
Too
That's
bad
right.
Brittany's not here, she would love this.
Who's that? Brittany?
Brittany.
Oh, she was here. She came to second.
Oh.
She skipped personal finance.
Oh,
She
did
did,
personal
yeah, she
finance
did
too.
it. She did it.
Personal finances.
She did it. All right. We do not do a lot of work in here with the theory. We just assume a lot of the stuff that I tell you. We don't get into a lot of the theory of it. But we're going to get into a little bit of it here at the end of chapter 4. So we're going to have a few theorems. And the title of this section is, why does continuity matter? Why is it important if you know that a function is continuous? Okay, what does that do for you if you know a function is continuous? Which basically means no holes or breaks or gaps, that kind of stuff. Well, one of the things that it helps is with something called the extreme value theorem. So one of the questions on next week's quiz is going to be, state the extreme value theorem. That's going to be a question. Okay?
I can do that.
So you absolutely can, those of you that like to make a note card and memorize, you will love this question. Here's what it says. Let f be continuous on a closed interval AB. Or you could say, if f is continuous on a closed interval AB, then, hypothesis and conclusion, like the old if-then statements, right? Hypothesis is the first part, conclusion is the last part of the result. So if f is a continuous function on a closed interval, then f assumes or has or will have or whatever both a max value and a min value somewhere on the interval AB. This is called an existence theorem. This just guarantees that if certain conditions exist, then something will happen. So if the function's continuous on a closed interval, then there will be both a high spot and a low spot. Would be a little more ordinary everyday language, but we should say max value, min value. Now, we also know, and this would also be another perfectly good question for the quiz next week, we also know that if we have this situation, where would we look for those max and min values? Derivative 0 at the endpoints, and where the derivative is undefined. There's 3 places we would look, where the derivative is 0, derivative is undefined, and endpoints. Now this theorem doesn't say anything about where to look. This just guarantees it'll be there. Now, we also saw some problems that had a global max but didn't have a global min. Well, they weren't continuous, or maybe it wasn't a closed interval. Some points we didn't have endpoints, right? Some problems we didn't have endpoints. So in those problems, where we only had one candidate, right, those would not be covered by the extreme value theorem. Like a parabola doesn't have a maximum unless you put endpoints on it, right? So that's the thing about a hypothesis. The hypothesis part has to be correct for the theorem to hold. You guys that were in computer math, remember our example? If you get an A, your parents will buy you a car. Wouldn't that be nice? But let's say that was the promise. Because that's what a theorem is like a promise. It's a promise that says if the function's continuous on a closed interval, it promises that there will be both a max and a min value. Okay? So if you get an A, your parents will buy you a car. Okay? The hypothesis is you get the A. The conclusion is that they'll then buy you a car. So we talked about this in computer math. We said, well, let's go through the possibilities. What if you get an A?
Okay.
They buy you the car, right? Or else they broke their promise. And we can't break this promise. This is proven to be true, right? So if you can figure out a way to something that breaks this, let me know. We'll all get famous, right? I'll take credit for it. I'll take credit for it.
Isn't that a thing though in college? If you
Yeah, the grad assistant or whatever comes up with something, and the professor publishes it for us.
That is
Um,
very nice.
I don't know if that's true, if you could do that, but I think it's probably happened.
Yeah,
I suppose if they're working underneath, yeah,
you can do it legally.
yeah, no,
It will
that's
usually
right.
be like this person.
Yeah, and most of those kinds of discoveries aren't just one person, right? But that's the promise. But here's where it gets interesting, and you're going to have some homework questions on this. So obviously, if you get the A and they don't buy you the car, then they've contradicted what they said, and that broke the promise. But where it gets interesting is, what if you don't get the
You might
A? You
still get the
still
car.
might get the car, right? That if you don't get, now we all understand that if your parents said, hey, if you get an A, I'll buy you a car, that they also mean if you don't get the A, you're not getting the car. But if that's what they say, if you get an A, then I'll buy you a car. If you don't get the A, they can still buy you the car and not have broken the promise, right? So, same thing is true here. If a function is continuous on a closed interval, then we know it has to have both a max and a min. That's the promise. But what if the function is not continuous? Could it still have a max and a min value? Sure, right? But it wouldn't have to. There's no guarantee. If you don't get the A, you might get the car, but you might not. There's just no guarantee. Well, same thing is true here. So on the homework, there's going to be some problems where they're going to give you a function that's clearly not continuous. It's got breaks and gaps all over the place. And it's going to say, does the conclusion hold? In other words, is there a max and a min? Because there could be. And so you'll look and you'll see if there is. And if there isn't, then you'll say, no, it doesn't hold, or yes, it does hold. But it won't violate the theorem if it does hold, or if it doesn't hold, right? So it'd be like this. If you had a function that did this, okay, here's the high spot, here's the low spot. If I put a hole right there, is that function continuous? No. But does the conclusion hold? Is there still a max and a min? Yeah, there still is a max and a min. Now, if I put the hole there, is there a max on that function? There is no max value on that function. Let's say that was 3, where the hole is. What would the max value be? There isn't one. I mean, if you say 2.9, I'd say 2.91. If you said 2.999, I'd say 2.9991. Right? No matter what number you get close to 3, I can always get another one closer. Right? There is no max value on this function, but that doesn't violate the promise. Right? Because this is not a continuous function, so it's not guaranteed to happen. But it might. Okay, so there's going to be some questions in there with that kind of language, and so I want you to understand what it is they're talking about in those questions. Okay, let's do the next one. So that's a pretty simple one. Let's do the next one. This one's a little trickier to understand. This one is the intermediate value theorem.
I don't like this one. It's a big game.
All right. So now when you hear the word intermediate, what comes to mind? Not quite middle, but yeah, that's okay. Yes, that's true. In between. In between. Not necessarily middle, but in between. Okay? And I guess by middle I think halfway, but so it wouldn't have to be halfway, but anything in between is what we want with intermediate. Okay, and that's what it has to do with. So the names kind of give it away. Extreme value, so that's how you can memorize them, obviously. Extreme value talks about the extremes, the high and the low. Intermediate is going to talk about in-between values. Here's what it says. If f is continuous on the closed interval AB, or let f be continuous, okay? The word function's not in there. I just noticed that. I probably should have said let f be a continuous function, but if you say it like this, that's fine. And you don't have to state these word for word. Although, I do want to caution you, I'm going to talk about them a lot in kind of common ordinary language, but yet when we state them on the quiz, I want it to be in the more mathematical language here, okay? But to help understand them, we'll kind of use some more common language. So let f be a continuous function on the closed interval AB. So you notice that same kind of thing there in the hypothesis. But now we're going to add to that. And let k be any number between f of a and f of b. All right, now, what's f of a and what's f of b? The outputs,
At A and the output at B.
When the input
Which-
is A.
which are the endpoints, right? So it's the outputs at the endpoints. Sounds weird. Right? That's very critical you understand it. F of A and F of B are the outputs at the endpoints. Okay? Because A and B are the two endpoints, right? So F of A and F of B are the Y values. So K is any number between F of A and F of B. So K is a Y value between the Y values at the endpoints. Okay? So that'll be important here in a second to understand. All right, then there exists, so the conclusion now is, then there exists some C between A and B, so those are inputs. There exists a C in between A and B such that F of C equals K, such that the output equals that output between the endpoint outputs. Okay, well, you'll see. When we draw a picture, we'll draw a picture of it and we'll clarify this, okay? But one of the downsides to using more common language is it's not as precise. And so we really need this mathematical language. It is important. But to help us understand it and picture it, we're gonna talk about it here. All right, everybody got that? So here's what we're saying. Let's say we have a picture here, and we've got this graph like so. Now here is F of A. And here is F of B. Right? We said that K could be any value between F of A and F of B. Now it's important to understand here, and this is one of the places people get confused on this theorem, is they think that it means between the high and the low. It does not. This doesn't have anything to do with the max and the min in this problem. Okay? K is any number between F of A, the starting point, and F of B, the ending point. Okay? It says, then there exists some C in between A and B where the output is equal to that K value. So it's like this. K can be any value in between here. So what if K was this value? There has to be some point that has that as its input. Oh yeah, there it is, right there. Oh, there's also another one over here, right? Or what if K is this Y value in between F of A and F of B? There has to be some value. Sure enough, here there's actually a couple of them. There's actually about 3 of them here. Does that make sense? In other words, here's another way I would say this. That if a function starts here and ends here, that function has to go through all the Y values in between those two. That's basically what this is saying. If a function's continuous, if it starts here and ends here, it's got to hit all the Y values in between them on its way. Now, doesn't that seem to make perfect sense? Right? We used this without knowing it the other day when we were doing Newton's method. We were looking for roots. And we said, we plugged in f of -1, I don't remember what we got. Let's say we got 5. And then we plugged in -2. Now we were hoping to get what? 0. Newton's method, right? We wanted to find where the output was 0. So we plugged in -1 and got this. We plug in -2 and we get this. What do we know?
That 0 has to be.
It had to hit 0 somewhere in there. Now, that was quite a leap on our part of assuming that. Because what if that function would have been 5 and then jumped down to be -7? How did we know it didn't do that? Because it was a polynomial function, and polynomial functions are continuous. So that's really where this theorem comes in. Because of the intermediate value theorem, it tells us that if you have a continuous function and you start at this Y value and you end at this Y value, I know I had to have hit all the Y values in between, so it had to have hit 0 at some point. Maybe more than once, but I had to hit 0 at least at one point. We were using the intermediate value theorem when we did that. Okay, so we're getting into the theory of it a little bit here, but that's what it's saying. But again, the peak doesn't matter. it just says I hit all the Y values in between. It'd be kind of like this. If I'm going on Highway 30 and I start in Kearney and I end in Grand Island. Now that's all you know. Start in Kearney, end in Grand Island. We'll assume this is continuous, that I do not have warp or beaming powers like in Star Trek, right? I can't just beam myself from one place to the other. So it's continuous. So I start in Kearney, end in Grand Island. What's that tell you? I had to go through Gibbon and Shelton and Wood River. Did I have to go through Elm Creek?
No.
Could I have went through Elm Creek?
Yeah.
Sure. Right? Started in Kearney, ended in Grand Island. Could have went this way. Yeah, why would I go? Why would anybody go? So, started in Kearney, I could have went to Elm Creek, I could have come back this way, could have went to Grand Island, went past Grand Island, came back to Grand Island, right? All we knew is we started here and ended here, we had to hit all those points in between. Could have hit some other points, but we know we had to hit all those points in between. Okay, and that's what this is saying. So it's really key, that F of A, F of B is important. It's between the endpoints, not between the high and the low. All right, so again, you're going to get into some of these functions. If you've got a function that's not continuous, it still might hit all the points in between. But it's just not guaranteed to, right? It's just not guaranteed to. All right, so again, I can put up that one I had a minute ago, you know, where it goes like this, and it goes like so, and it's got a hole right there. This is not a continuous function. But does this function hit all the Y values between those two right there? Yeah, right? If this was your, so here's F of A. I'm recording and they're not seeing this. Here's F of A, here's F of B. Does it hit all the Y values in between there? Yes, it does, right? Even though it's not a continuous function, okay? Yes?
I don't know why
When
you
did
drive.
you realize that you something else?
You're going to have some examples in your home of that very thing. But since you asked those questions, if I was driving and when I passed a certain point, I was going 10 miles an hour, and 5 miles later, I was going 60 miles an hour. What do you know? You were going at some point in time, you were going every speed between 10 mile an hour and 60 mile an hour. Right? Right? Okay. But your question was, when is one that's not continuous, right? Because that would be continuous. Okay? Oh, here's a perfect one. This is applicable to this one. At the starting point, we had 44 people in calculus.
Okay, this is a great example. I see where you're going with this.
And today, we have 34 people in calculus. Is that continuous? If that was continuous, what would that mean?
Then one by one.
And at every point in time, we had to have every number between 34 and 44 people in calculus, including decimals. Right? Including decimals.
So
we
what
had
you're
to-
telling me is that it's slowly starting to dissolve.
Slowly started dissolving or something, right?
That's
Because,
basically what calculus
yeah,
does.
because number of people is not continuous. It's discrete by ones. It'd be like dots as opposed to continuous curves. So those would be examples, yeah. Matter of fact, that's a term, discrete versus continuous. It'd be like a digital clock that goes 1 minute, then 2 minutes, and 3 minutes as opposed to, that one.
Oh,
That one's,
But the
but
ones that keep
the ones that
going,
just sweep, right?
those are
That would
really
be
annoying.
continuous as opposed to a digital. So there would be a lot of examples probably. I suppose money would be another one, right? Money would be another one. I had $20 in my pocket, and an hour later I had $10 in my pocket. Does that mean that every time in between there I had every amount of money between 10 and 20? No. Matter of fact, I think I just gave away some of the homework problems. I think, right there. So,
Oh,
good
dang.
question. All right, so that is it for today. So let's recap where we're at here with this. I've got a couple of things to hand out.
This right here.
This right here, thank you. All right, so So today, the homework is 4-8. It says right there 4-8, so it's a number of questions dealing with these two theorems. Okay, so 4.8 homework is for tomorrow. So that should be probably your main focus. You can do a little packet work if you want to, but for sure get the 4.8 stuff done. Okay, now, this is the take-home assignment. This will be handed in and graded. It will be handed in on Tuesday of next week at the beginning of class. Okay? So now, my intent is that most of your work for this would probably be over the weekend. In other words, tonight your assignment is the 4.8. Tomorrow, we'll go over the 4.8 stuff, but we won't do new stuff tomorrow. Tomorrow, I'll answer some more packet stuff. We'll talk about the homework questions, but it'll be a lot of just work time in the packet. Okay, now I'm going to go ahead and give you the third packet here. So tomorrow you'll get a work on the first two packets if you've still got work to do in them. And then also get started in these, but there'll be time in class tomorrow. Okay? So over the weekend, so Friday, tomorrow my assignment to you will be work on the take home and continue in this packet a little bit. Okay? On Monday, we will then, and I may give you a hint on number 4 of the take home. I may post that online this weekend. But otherwise, I'm not really going to help you much on the take home. Now, I think you can do number 4 without the hint, but that's usually one that some people ask some question about, so a lot of times I give just a little bit of a hint on that one. I'll probably put that on the website this weekend. So then on Monday, we will probably talk about the last section. We have one more theorem to do. That's the mean value theorem, and we'll talk about that on Monday. So it'll be an assignment with some of that, fairly short. So you'll be continue to work on packets. Then Tuesday, we'll review all that. We'll hand in the take-home. So if you didn't get it done over the weekend, you'll still have Monday night. But you'll have a book assignment too, so you'll want to make sure not leave the take-home till Monday night. That wouldn't be a good idea. Well, unless you have no other option. You know, some of you that have a busy weekend, I know. But then on Tuesday, we'll review for that the no calculator quiz and those kind of ideas, and then that's going to be on Wednesday, and we'll continue working on packets, and then on Thursday will be all packet work day, and then probably midterm Friday and Monday. Time of the plan. So the next 10 days be pretty busy with those kind of things. Okay? All right. So anyway, so you can plan accordingly. What's that? 2 days. 1 day's a calculator day, 1 day's a no calculator.
Will it take us a solid 90 minutes?
No, actually, it's timed like the AP test. So what I do is I based on the number of questions I time, because on the AP test that first section that's 28 that's 28 questions, they give you 55 minutes for that. So that's about 2 minutes a question. The second section, which is 17 questions, that's the calculator multiple choice, they give you 50 minutes. So that's about 3 minutes a